Hi, hello. This video is about op-amp or operational amplifiers practical applications. Okay, so to start with, we have here the the inverting amplifier, or what we call the negative scalar. Okay, so inverting amplifier, so your operational amplifier can work as an inverting amplifier or a negative scalar. So this is a closed loop gain of of the inverting amplifier depends on the ratio of the two external resistors, which are your R1 and your RF. Okay, and it is independent of the amplifier parameters. Okay, so that means it doesn't matter if your amplifier or your op amp is 741 or other type of op amps. Okay, but when we connect it in an inverting amplifier mode, so the gain will only be determined by your R1 and your RF. Okay, so it means it scales the input or it multiplies an input. So it's like a multiplier. Okay, so it scales the input, it multiplies the input by a minus constant factor of k. Okay, so this is our representation for an inverting amplifier. So this is your feedback resistance and this is your R1 or the internal resistance. So for inverting amplifier, our input is being placed or being applied at the inverting terminal. So for 741, our inverting terminal is your pin number 2. Okay? So your non-inverting input is grounded. So our formula for the voltage gain is the output voltage divided by your input voltage. Okay, so that is equivalent to negative RF all over 1. So from our previous video, we have already derived why it became negative RF all over R1. So your RF all over R1 can be represented by a constant. Okay, so let us call that K. So that means your input voltage can be multiplied K times. Okay, so K times. But we have a negative sign here showing that there is a 180 degrees out of phase between your input and your output signals. Okay? So, another application for our operational amplifier is as a non-inverting amplifier, or what we call the positive scalar. Okay? So, this is used when there is a need for an output which is equal to the input multiplied by a positive constant. Okay, so positive scalar circuit which uses negative feedback but provides an output equals the input multiplied by a positive constant. So there is no 180 degrees phase reversal, or your output is in phase with your input. Okay, so this is our representation for a non-inverting amplifier. So we apply your input voltage as at the non-inverting terminal. So if we are using the 741 operational amplifier, this is your pin number 3. Okay, so this is still your feedback resistance, which is your RF, and this is still your R1. However, our inverting terminal here is grounded. Okay, so our voltage gain still equal to V output divided by V input, and our value for our gain is equal to R1 plus RF divided by R1, or we can simplify that as 1 plus RF all over R1. So this is our gain for a non-inverting amplifier. Okay, now we have discussed that when your input is placed at the non-inverting terminal, okay, so our inverting terminal, if our input is placed at our inverting terminal, our non-inverting terminal has no resistance, or it is simply grounded. Or if our input was placed in the non-inverting terminal, the the input voltage is directly coupled to your operational amplifier. However, in practice, we have this what we call bias compensating resistance. So if you can still remember from our previous video, okay, so there are such things as our input bias currents and our input offset currents that are already within your within your operational amplifier. So what does that mean? So it means that even though we do not have any input yet, we can already read something at the output. Okay, so there is already an output voltage even though we don't have any input signal, and we don't like that. Okay, so but we cannot totally remove those because those are already inside, okay, or within your operational amplifier. So what can we do is by applying a potentiometer, okay, so that is our nulling resistance, and another thing is by applying what we call the bias compensating resistance, okay, or our RC. Okay, so our RC represents all or a portion of the source resistance. So the exact value of RC is not critical because we do not usually make use of your RC in computing for your gain, okay, and the closest standard value is usually sufficient. Okay, so for example, this is now our inverting amplifier circuit. Previously, this is just grounded, but in actual, okay, in practical applications, we place here an RC. So what is the value of our RC in our design? So your gain will still be dictated by the value of the RF and our R1 here, but your RC here is just the parallel combination of your RF and your RL. So in case there is no exact standard value for this parallel combination, so it is okay. We just have to choose the closest standard value. Okay, so this is now the new representation or the new schematic diagram for our non-inverting amplifier. So previously we don't have any resistor here. It's just directly the input is just directly connected to the non-inverting terminal of your op amp. But in practical use, we place a biasing compensating resistance, and that is still equivalent to the parallel combination of your RF and your RI. Okay? So we have here some design considerations, okay? So a summary of some of the major considerations of the simplified design approach to operational amplifier, small signal amplifier circuits are as follows. So number one, be sure that the dynamic range of the op-amp based on power supply levels with some back-off will be sufficient for the desired output signal. So that if you can still remember for 741, you can make use of a power supply having a value of positive or negative 12 volts. So since your operational amplifier is dual supply, so you have a positive and a negative voltage, so it can be positive 12, okay, plus or minus 12. It can be plus or minus 9 volts. It can be plus or minus 15, plus or minus 18, okay. So in your design, you should be aware, okay, on the actual power supply level. So for example, you need in your design to have an output equivalent to 12 volts, okay. So if your output must be equivalent to 12 volts, you will not be using any value which is lower than 12 volts or even exact 12 volts. Why? Because we discussed on our previous video that there are some back off, okay, for that specific voltage. So if we have for example, 12, maybe we can have a maximum output of just 10 volts, okay. So if you will be needing 12 volts, it will not be sufficient. So if we will be needing an output which is equal to 12 volts, better we make use of a supply which is equivalent to plus or minus 15 or plus or minus 18 and so on. Okay, so your design must be practical. So your design must be what do you call this? You have to use the proper power supply levels in your desired output signal. Okay? So number two, whenever possible, choose resistance values in the range of 1 kilo ohms to 100 kilo ohms. Okay? So our Ideal value from our previous video was 10 kilo ohms, okay? So, except avoid resistances that load the output in the lower portion of the range. That means values of 10 kilo ohm and greater are most widely used for many applications, because if we make use of a lower value, um, our back off in our power supply will also become lower. Okay, so if our 15 volts, for example, will give us an output of positive plus or minus 13 volts, if we make use of a resistance which is lower than kilo ohms, we might get a lower supply voltage. Okay, so number 3, you have to limit the magnitudes of closed loop gain to values much smaller than the available open loop gain. So that's the main purpose of our feedback resistance. Okay, so that is the reason why we place a feedback resistance, so that we can lower down our open loop gain, which is equivalent to 100,000 for an operational amplifier. So typically, closed loop gain magnitudes are kept under 100. Okay, and finally, we have to check the maximum output current levels under worst case condition. Okay, so each operational amplifier has its maximum output current. So for 741, so it is 25 milliamperes. So we might we might use, okay, a maximum current greater than its level, its maximum level, okay, which can destroy or ruin your operational amplifiers. Okay, so for the resistor values, these are the most widely used. So these are, you must at least be familiar with these values. Okay, so this is the most widely used resistors. Okay, so they are low powered axial lead, carbon composition, and film resistors with tolerance of 5% and 10%. Okay, all the values listed are available in 5% tolerance, but only the bold-faced values are available in 10% tolerances. Okay, so if you can still remember your resistor color coding. Okay, so what do we mean by this? So when we say 10, so this is available in 1 kilo ohm, 10 kilo ohms, 100 kilo ohms. Okay, so 10k, 1 mega. Okay, so those are in those following range. So you have 1.5k. Okay, so you have 15k. Okay, so 150 kilo ohms, like that. Okay. So for other applications, practical applications such as instrumentations, okay, wherein we are very particular with our design, and we do not want any variations or high variations in our design. We also have resistor values in 1% tolerances. Okay, so if you're going to make use of these resistor values, so they have a tolerance of 1% only. So therefore, you have the possibility of getting an accurate circuit is higher because your tolerance is very, very small. Okay, so usually these are being used for instrumentation purposes. So the design problem, actually design problems are not very, very difficult, because when you say inverting amplifier, you have already the design for an inverting amplifier. You know already what does an inverting amplifier looks like. Okay, so when we say design, actually you're just placing your value of RF and R1 in such a way that you are asked for. Okay, so what must be the value of RF and R1 that is being required in the design. Okay, so we have here an example. Using a 5% resistance values, okay, design an inverting. So VCVS is a voltage controlled voltage source amplifier, okay, to provide a voltage gain of -10. So we want a voltage gain of -10. And what are some other considerations? So it says here that the input impedance must be no less than 10 kilo ohms. Okay, so therefore our minimum requirement is 10 kilo ohms. to avoid loading the given signal source. Okay, so the signal level will be sufficiently high to the thermal resistance noise, and the bias current effects are not felt to be a critical problem, provided that the resistance values less than 500 kilo ohms are used. So therefore, we are given a very broad range of resistances that we can actually make use of. Okay, so it just says here that it must not be less than 10K, okay, or it must not be greater than 500K. Okay, so but as long as it is within the range, your design is correct. Okay, so you don't have to worry as long as you can comply with the requirements. Okay, so this is an example. This is just one example of the design for that specific problem, because our requirement there is you have to have a gain equivalent to -10. So since there is a negative already in our requirement, so we already know that you are going to make use of an inverting amplifier, because if you have an inverting amplifier, automatically you get the negative gain there. Okay, so the only problem is what combination of RF and RI are you going to make use of so that you can have a value which is equivalent to 10. Okay, so our formula for the voltage gain for your inverting amplifier is equivalent to negative RF all over R1. So you must use a value of RF and R1 in such a way that if we divide them, your answer will be equivalent to 10. So in this case, it make use of 220 kilo ohms all over um, 22 kilo ohms. So automatically we have the negative sign there. So 220 divided by 22 kilo ohms. So that will give us a gain which is equivalent to -10, which is your required gain in the problem, in your design problem. Okay, so the 20 kilo ohms there, okay, where did it came from? So the 20 kilo ohms there is your compensating resistance, and your compensating resistance is just the parallel combination of your RF, which is 220 kilo ohms parallel your 22 kilo ohms here. Okay, so if you solve for that, so that is 220k times 22k divided by 220k plus 22k. So that will give you an exact value of 20 kilo ohms. So luckily, these are all available. So if we're going to look back, okay, so if we're going to look back at our resistor values, where is that? So this is your value, 220 kilo ohms, and make use of 22 kilo ohms. Actually, we can make use of where? From this 22 up to 51 here. Okay? So we cannot we can also use this one. So we can use 100 kilo ohms divided by 10k. Okay, so this is included in our this is included in our option. Okay, so you can also make use of 150 kilo ohms and 15 kilo ohms for your R1, so that can still give you a gain equivalent to 10. So you can make use of 470 kilo ohms and 47 kilo ohms. That will still give you a gain which is equivalent to -10. Okay, but can we use the 56 here? So if we make use of the 56 here, you can have 560 kilo ohms for your RF and 56 kilo ohms for your R1. However, it says in the problem that we must not exceed 500 kilo ohms. Okay, so therefore, we are only permitted to use up to 470 kilo ohms and 47 ohms. Okay, so in a design type of a problem class, you can have several answers. Okay, so you can have several answers as long as you follow all of the conditions, okay, that is asked in the design problem. So no problem. So there is no such thing as a wrong design as long as you follow all the specific conditions. Okay? So we have here, using the standard 1% resistance value, design a VCVS non-inverting. Okay, so what do we mean by non-inverting amplifier? So in this case, we have to place your input at the non-inverting terminal. Okay, so to provide a voltage gain of 18. So remember that for a non-inverting amplifier, your gain, okay, so your voltage gain is equal to RF all over R1 plus 1. So we need to get a combination, okay? So you have to have a combination wherein your RF all over R1 must be equivalent to 17. Okay, so that if we add them, your resulting gain is 18. And the positive answer there, or the positive gain there will be what do you call this? uh, will be possible if we make use of a non-inverting, because the gain for a non-inverting amplifier is positive. Okay, so in this case we have an example. So we have here 2 kilo ohms, we have 34 kilo ohms, and we have here 1870 ohms. Okay, so if we divide 34 kilo ohms by 2, so we will be having 17 for that. Okay, then 17. So we have here 34 kilo ohms divided by 2 kilo ohms. So that will give you 17 plus 1. So that will be equivalent to, equivalent to 18. Okay, and then for the compensating resistance, all we have to do is to get the parallel combination of 2 and 34, okay, which is 1870 ohms. Okay, so if we're going to look at those values here, so we have 34 kilo ohms. So where is your 34 kilo ohms? So this is your 34 kilo ohms. So where is your 34 kilo ohms? This one. So 340. So this is 34, and this is your 2 kilo ohms. So where is your 2 kilo ohms? Here, 200. And then we have the 1870. Okay, so we have 1870, 1870. So we have a 1870. So luckily we have all. But when you get the parallel combination and you didn't get any exact value, it's okay. All you have to do is to get the one with the nearest value. So you can have any other answer. Okay, so you can look at this value, and then as long as it will give you a gain of 18, that means you will have a ratio which is equal to 17. Therefore your answer is correct. Okay, so our non-inverting amplifier is the counterpart of your common base configuration for our BJT amplifiers, or the common source, also common gate configurations for FET. Okay, and then the inverting amplifiers, okay, is the common emitter configuration for BJT, or the common source configuration for FETs. Okay, so we have another type of application, so wherein we call this as your voltage follower or unity follower. Okay, so voltage follower or unity follower provides a gain of unity without any phase reversal. So what is your output, what is your input, that will also be your output. Okay, so this is useful as a buffer or isolation amplifier because it allows input voltage to be transferred as output voltage, while at the same time preventing load resistance from loading down the input source. Okay, so in your logic circuits, if you have, this is the opposite of an inverter. So an inverter will give you the same output amplitude, okay, or magnitude, but with a phase reversal. Okay, so if our input, for example, is -1, your output is +1. So for voltage follower or unity follower, so it is a buffer. Okay, so when you see block diagrams having a buffer, so you can make use of an operational amplifier for that. So if our input is 1 millivolt, your output is also 1 millivolt. Okay, so this is just being used for electrical isolation purposes. Okay. So how do we connect operational amplifiers in such a way that it will be functioning as a voltage follower or a unity follower? So this is your connection. Okay, all we have to do is to place an input at the non-inverting terminal because we have to have the same phase reversal. So our input must be placed in the input terminal, and then this is our output. Okay, so you just have to place a ground between your inverting terminal and your output for your feedback. So it is just like that, for example, our input here is, so for example, we have here your operational amplifier. So let us call this your VA, okay? And then let us call this your VB, wherein your VB, this is your non-inverting side. So this is your input voltage, okay? This is your feedback here, and we have here your output. Okay, so always remember that if we make use of this configuration, your RI, okay, so your RI is infinite. Okay, so we don't have any input here, we don't have any input resistance, so this is infinite. And our feedback resistance is what? This is shorted, so this is equivalent to 0. Okay, so in this case, we can say that your VA is equal to your V out. Okay, so if you were going to remember our voltage here, virtual ground, so the difference between VA and VB here must be equal to 0. So to do that, our VA must be equal to our VA must be equal to VB. Okay, so but our VB is equal to your input voltage, okay, which is your V in. But your VB is equal to your V in. Okay, so your VB is equal to your V in and your VB is equal to VA. So that is your V in is equal to your V out. So in solving for the voltage gain, okay, so your voltage gain is V out all over V in, and since they are equal, your voltage gain is equal to 1. Okay, so if you wanted a buffer circuit, so in our communication subject, we can see block diagrams having buffer circuits in their blocks. So one option is to make use of an operational amplifier. Okay, so what is its corresponding counterpart for BJT? So this is just like your emitter follower or our common collector configuration, because in our common collector configuration or our emitter configuration, that is in phase and no voltage gain, or your V out is approximately equal to your V in. Or for FET, it is equivalent to your common drain configuration. Okay, so that is the third practical application of your op amp. So you just get your op amp, you place an input, okay, so you put an input voltage at the non-inverting terminal, and then you place a wire, okay, shorting your inverting terminal, and your output here, you can have your inverter with you. Okay, so we can place some resistors here. So these resistors here are for compensating resistors only. Okay, but anyways, it will give you the same expected output. Okay, so another practical application for our operational amplifier is adder or summer. Okay, so what is adder or summer? Okay, we have here, this provides an output voltage proportional to or equal to the algebraic sum of two or more input voltages, okay, each multiplied by a constant gain factor. So this is basically similar to a scalar, except that it has more than one input. Okay, so for example, this is our circuit for an adder or a summer. So you will make use usually of a inverting amplifier, but instead of having just one input, we have several inputs. Okay, and then our sum is our output rather is the sum of all the input voltages here multiplied by a certain factor. Okay, so how do we evaluate this type of circuit? Okay, so for this type of circuit, okay, so let's just say we have several currents that will pass through your operational amplifier. Okay, so those currents will can be added up using the total current, which is your I1 plus your I2 plus your I3 here. Okay, so we have here, but what is your I1? Okay, so our I1 here is equivalent to your input voltage V1 at that terminal, okay, divided by your certain resistance R1, okay? And then we have here your I2, but what is your I2 there? So that is equivalent to the voltage that is being applied across the terminal divided by your R2. And then what is your I3? So the voltage across the terminal, which is your V3, divided by your R3 here. Okay, so that is our answer. Okay, so if you're going to remember what is our V out, okay, for an inverting amplifier, because that configuration is an inverting amplifier because we place all the inputs at the inverting terminal. So that will give us minus RF all over R1 multiplied by our input voltage. So that is your output voltage. So if we combine them, okay, so if we combine them, we can have your total output voltage, which is equivalent to minus, okay, that is your RF. Since RF, feedback resistance, is common to all of your inputs, so your RF there will be, so your RF there is equivalent to, sorry, RF all over R1 multiplied by your input, which is your V1. We have here plus, okay, RF all over R2 multiplied by your V2. You have here plus RF all over R3 multiplied by V3 here. Okay, so that is depending on the value of your R1, okay, but you have the same RF and R1. Okay, so if we wanted to simplify, okay, so if we wanted to simplify your circuit wherein each of the value of R are equal, okay, so let us say your R1 is equal to your R2, that is equal to your R3, and that is equal to your RF. We can simplify this further by having minus, okay, R, let us just call that R, all over R, multiplied by V1, okay? So we have here your R, all over R, multiplied by V2, plus, let us say, you have here R all over R multiplied by V3. Okay, since our R is constant, we can put it outside, and that is R over R. So this is constant, which is equivalent to 1. So that will give you a V1 plus V2 plus V3, which is our output voltage. Okay, so as we can see, what did we have here? So we have a sum of all the input voltages. So V1 plus V2 plus V3. So this is your adder. Okay, so usually In practical applications, we have here your mixers, for example. So you have your mixers wherein, for example, you have you wanted to have a microphone, and then you wanted to have a guitar, for example, or a piano, for example, and you wanted to blend the music, or you wanted to amplify the microphone further so you can hear the voice compared with the auxiliary input, for example. So you can make use of a adder or a summing amplifier. Okay, so this is your application for adding or summer. Okay, so this is if simple addition or inversion is desired. Okay, so your compensating resistance here is still equivalent to the parallel combination of all the resistors that you can find in the circuit. Okay, so that is the definition for your compensating resistance. Okay, so what are an example? Okay, let's have an example. So we have here, in a certain application, it is desired to combine two signals V1 and V2 to form a signal VO according to the following combination. So your VO must be equivalent to negative V1 minus 10 V2. Okay, so the minimum input impedance for both inputs should no less than 10K. So design a circuit to to meet the requirements. Okay, so how are we going to solve for that? So how are you going to solve for that? So actually, class, we have here your answer. Okay, so you have two inputs. Okay, so we just have to make sure. So we just have to make sure that, okay, so we just have to make sure that we can have this output. So VO must be equivalent to negative V1 minus 10 V2. Okay, so since you share the same RF, okay, so we have to make sure that your V1 will have a gain which is equal to 1. So that is equivalent to 100 divided by 100. So that is equivalent to 1. So this is negative, okay? So we have here um 100 kilo ohms divided by 100 kilo ohms. So this will give you a gain which is equivalent to 1 times V1. And then you have to choose a value that when you divide it by 100, the answer will become 10. Okay, so that is 100 kilo ohms here divided by 10K. So this ratio here will give us a value which is equivalent to 10 multiplied by our V2. So in this case, so that will give you minus V1 plus 10 V2. So that is your design considerations. Okay, so if you might be wondering, can I choose 200 here? Yes, but you have to use 200 here. Okay? And if you choose 200 here, you have to use 20 here. Okay? As long as you can have the required design um, problem. Okay? So you have many options. Okay? So you have many options. Now, what is your RC there? Okay, so where did the 8.33 kilo ohms came from? So that is just your 100K parallel 100K parallel 10 kilo ohms. So all the resistors that you can see there in your circuit, that will be that will cover your compensating resistance. Okay? So I have here a problem, and that will serve as your activity, okay? So it says here, in a certain signal processing system, okay, it is necessary to combine and modify the levels of three signals V1, V2, and V3. So the desired VO is 2V1 plus 5V2 minus 10V3. Okay. So what we need is a non-inverting output. Okay, since this is positive. But it says here that you can make use of linear combination circuits and or inverting amplifiers only. Okay, so you might be wondering, this is positive. So I will be using a non-inverting amplifier so that I can have a positive answer. But it says in the problem that you are to use only inverting amplifiers. Okay. And also, so I need a positive output. So if that is an inverting, I will be placing a negative input. Okay. But it also says here that you are not to use. Okay, so do not use negative voltages as input. So you have to use only positive input. So you have to design. Okay, so you have to design using inverting amplifiers. Okay, so in the design, no, nothing is wrong as long as you can get this output voltage. Okay, but you have to take into considerations that you will be using inverting amplifiers also only, but you can have more than one. Okay, and you have to make use of positive inputs only. Okay, so this is your task. Okay, and I want you to answer this uh, using our using what you have learned from our discussion. Okay, so this is one application. Okay, so this is one application for our operational amplifier. Okay, so it can be used as a positive scalar, it can be used as a negative scalar, it can be used as a unity gain, okay, or a buffer, and then it can be used as a summing amplifier, okay? And then what will be our next? So our next is if it can add, likewise, it can also subtract. Okay? So if it can add, it can also subtract. Okay, so what are we going to make use of? Where are we going to place the input so that we can have your operational amplifier work as a subtractor. Okay, so a subtractor or a closed-loop differential amplifier is used to provide an output proportional to or equal to the difference, okay, subtractor, to the difference of two input signals. So this time, your inputs are supplied both at the inverting and the non-inverting terminals. Okay, so for summing amplifiers, all of your inputs are being placed only at the inverting terminal. So if we wanted to make use of your op-amp as a subtractor, therefore, we have to place an input both to your inverting and to your non-inverting terminal. So how does this look like? Okay, so this is your subtractor. Okay, so you have an input. So if you have a non-inverting amplifier, this V1 here is grounded. If you have an inverting amplifier, this V2 here is grounded. Okay, if you have a summing amplifier, all of the inputs V1 and V2 are being placed at the inverting terminal. If you have a buffer, okay, our input is in this one, and then we just have to place a wire between the inverting and the output terminal. Okay, so for a subtractor, we need to place an input both at the inverting terminal and the non-inverting terminal. Okay, so how do we arrive with this V2 minus V1 here? Okay, so if you're going to remember from your circuit analysis, okay, so we have what we call the superposition theorem. So what does the superposition theorem um, function? So how does the superposition theorem functions? So we're just going to work on only one input terminal at a time. Okay, so that means when we are dealing with your V1, so we are going to place your V2 grounded. And at the same time, when we're dealing with V2 already, we are going to ground your V1. Okay, so let us start first with V1. So when we are working on V1, okay, so that means your V2 is grounded. So when your V2 is grounded, okay, so when your V2 is grounded, it's just like you're working on as an inverting amplifier. So when you are working as an inverting amplifier, okay, so V1 is acting alone. So that is an inverting amplifier. So that will give us an output. So let us call that output as VO1. Okay. So your output is a is an inverting amplifier, and that is equivalent to RF all over R1 multiplied by your V1. Okay. So this is just like an inverting amplifier. So this is just like an inverting amplifier. Okay, so what if V2 acts alone? So that means we are going to ground your V1. So if we ground your V1, it is just like working as a non-inverting amplifier. So when you have a non-inverting amplifier, okay, let us call this VO2. Let us call this VO2, and that will give you RF all over R1 plus 1, okay, multiplied by V2. Okay. So for superposition theorem, upon getting the individual answers, we are going to combine them. So we're going to either add them or subtract them. But since this is of negative sign, so if we add them, we will be having a negative sign here. Okay, so for simplification purposes, we can just assume that your RF plus R1, RF all over R1 plus 1 is approximately equal to RF all over R1. Okay, so combining the two, so we have your V out, and your V out is equivalent to VO2 minus VO1. Okay, because of the negative sign there. Okay, or plus. So VO2 is RF all over R1 times V2 plus, okay, minus, but that's a negative sign. So we have RF all over R1 multiplied by V1. Okay, so factoring out your RF all over R1, we have here an answer which is equivalent to V2 minus V1. Okay, so if we are going to simplify this further, and let us say RF will be equal to R1, so we will be getting an output which is the difference. Okay, so we will be getting an output which is the difference between your two input voltage, which is your V2 minus V1. So we have a subtractor. Okay, so that is how your operational amplifier um, can be applied as a subtractor. So as you can see, just changing where are you going to place your input, you have several applications for your operational amplifier. So that means your operational amplifier class is very versatile. Okay, and it can add, it can subtract. Okay, so actually it was called operational amplifiers because it was really designed, it was really first designed to perform mathematical operations. That's why it was called operational amplifiers. Okay, so this is a very simple type of a subtractor. However, in practical use, we have here your practical application for a subtractor. Okay, so this is what we call, uh, this is how we design or how we use your actual subtractor class. Okay, so wherein we have four resistors here. Okay, so this is like a voltage divider for your V1 and your V2. Okay, so for example, we have here your V2 alone. For example, if we ground your V1 here, so it is working as a non-inverting amplifier, so we can get your first output, which is minus R4, which is your feedback, all over R3 multiplied by our V2 here. Okay? And if your V1 is acting alone and your V2 is grounded, okay, so the input voltage will be So the input V1 here will be divided between R1 and R2, and the input is the voltage across your R2 because this will serve as a voltage divider. Okay, so for VO2, okay, so let us call that VO2. So that is non-inverting amplifier. So we have 1 plus R4 all over R3, okay, multiplied by the input voltage. But what is the input voltage? So the input voltage is the voltage across R2. So we have a voltage divider between R1 and R2 multiplied by our V1 here. Okay, so that is your V2. So to get the total value, so to get the total output voltage, so that is a combination of your R3, 1 plus R4 all over R3 multiplied by R2 all over R1 plus R2 multiplied by V1. So minus, you have here R4 all over R3 multiplied by V2. Okay, so just what we did earlier. This time, we just have your voltage divider configuration here. Okay, so for instrumentation purposes, we make use of the balanced closed loop differential amplifier. So the balanced closed loop differential amplifier is the most important case of closed loop differential amplifier. So it is said to be balanced if we make use of these values. So your R here specifies a certain value that are equal, okay? And this A here specifies a gain. Okay, so the two gains are equal and opposite. So how are we going to attain this balanced closed loop differential amplifier? If we're going to follow these suggested values for R1, R2, R3, and R4. Okay, so if we're going to substitute this value in our equation here, so if we're going to substitute those values in our equation, so that will give us, okay, so your V out is equal to 1 plus, what is supposed to be the value of R4? R4 is equivalent to AR3, or let us call that AR, divided by R3, which is equivalent to R. Okay, and this is equivalent to what is our R2? R2 is equivalent to AR all over R1 is equal to R plus R2 is equivalent to AR. Okay, multiplied by V1. So this is R4. R4 is equivalent to AR minus AR all over R multiplied by V2. Okay? So we have here AR here will be canceled out. So I have here 1 plus A, and then I have here AR. I can factor out your R here. So this is equivalent to 1 plus A. Okay, so I can cancel out your R here, and I can cancel out your 1 over AI here. So I have a remaining A there for my V1 minus, I can cancel out your R there. I have here A multiplied by your V2. Okay, so your A can be factored out. So this is simply V1 minus V2. So our V out for a balanced amplifier is simply the difference. Okay, so that is simply the difference between V1 and V2 multiplied by a certain gain. But you have to make sure, okay, but you have to make sure that you follow this specific resistor requirement. Okay, so this is the derivation. So we have here an example. A circuit is desired for an instrumentation application in which the difference between two signals V1 and V2 is to be amplified by a factor of 10. So that is 10 V1 minus V2. Design a circuit to perform the required function. So the required function is that your A, so your A is equivalent to 10. Okay, so we have to choose a value for R. okay, which are similar to every values of our four resistors that is in our circuit, having a resistance which is equal to 10. Okay, oh, sorry, a gain which is equal to 10. So what is our answer for that? So we can make use of this one. Okay, so in this case, your R3 is equal to R, okay? And your R4 is equal to AR. Our gain is 10, okay? So 10 times 10, so we have here 10, 100 kilo ohms. So our R1 is equal to R, so let us say this is 10 kilo ohms, and then this is equal to 10 times R, which is equivalent to 100 kilo ohms. So can we make use of 20? Yes, we can make use of 20. So this is 20K, this is 200K, so this is 20K, this is 200K. So we can make use of 30, so this is 30K, this is 300K, this is 30K, this is 300 kilohms. So that is what uh, balanced closed loop differential amplifier operates. Okay, so don't forget don't be confused with the circuit, because the circuit is just the same. So when you say this sign, all you have to do is to change the value of your resistances. Okay, so there are more mathematical operations. So what else can an operational amplifier do? So aside from subtracting, aside from adding, aside from inverting, aside from multiplying, okay, so it can also integrate, it can also differentiate, and it can also compare. So we have an integrator, differentiator, and comparator, and I will be discussing that on the next video. Okay, so that's it for now. Okay, so I will be ending our discussion here, and wait for the follow-up video for the other practical applications of our operational amplifiers. Okay, so thank you very much, and don't forget to hit the like button after watching. Okay, thank you and God bless.